All right, wow. All right, thanks everybody. We got a good crowd tonight. Welcome to our Hack Night, which we've been hosting for a little over 10 years now. I'm Ben Sherry. I'm your host. I'm the founder and CTO of BigGestLab.io. BigGestLab.io. Check it out. And my co-host is Shane over here with Gummy Bear Consulting. He's responsible for the gummy bears that are here. And they are the top technical recruiting firm in Bangkok, in Thailand. And yeah, so we've been doing this quite a while. It's kind of a free-for-all technical theme, but it's all levels of tech. And tonight we're going to be talking about no hype AI. Because just like crypto, 90% of what you hear about AI is complete crap. It's all fabricated, it's nonsense, it's hype. But it's going to change the universe, just like crypto. So how do we figure out what's what? So we've been doing AI development for a little over 3 years. A lot of what you're seeing tonight is like third generation stuff that we put together where we found actual practical business cases for incorporating AI into systems that aren't just stupid chatbots and that aren't fully LLM based. Some of the things that we're going to point out, so it may look like crass commercial propaganda because they are products of ours, but we're going to show you what's behind them and why they are what they are and how that works. Also, FYI, next door behind us is Speakerbox, which is the best indie music venue in Bangkok. And tonight they're having a live jam session with a bunch of musicians in here, and the entry is free, and the drinks are cheap and plentiful. So I encourage you, after we're done with this, everyone retire over there and enjoy Speakerbox, because it's a really groovy scene. All right, so with that, and I didn't get to start recording on here. Oops. So my awesome introduction is forever missed on here, but we'll get it there. Shane, anything you want to say before we kick off? Okay. So yeah, so welcome everybody. So we have some things that we're showing off are products. Some things are experimental things, but they all have a theme of what we're trying to do. And the first thing I'm going to do a quick short demo of, and then show you the background and the architecture of it, is a tool that it is actually our first product that we released as Big AI, and it's called BigVault. And it's a content management and research system. And let's see if I can select this so I can go to the next page. Right. And it's basically, you can think of it as your Google Drive, right? It looks just like a Google Drive kind of thing, and you push up content to it. You can tag the content. There's something called a memory core here, and stick it in there, and then voila bing, you got a bunch of files, just like what you would expect. Nothing magic on there, but we have this concept called an AI memory core, which is a neat branding name because those words sounded cool. What's really happening is when you push like your PDF files up into it, we have a lot of background services that are watching this content and trying to extract and increase the value of that content. So in a PDF file, for example, it's going to take out all of the text. It will extract out all the text. And then it will vectorize that. And what that is, vectorizing or embedding it, is what happens when you're sticking something into an LLM. But instead of an LLM, we're putting it into a vector database. So this lets you do fuzzy searching of your content. And the way we make it is, depending upon what tags you have, it's going to go into different AI memory cores. So this is a way of you setting up different databases for different types of information in a completely ad hoc manner. You can change the tags, you can add new databases, delete ones. They can be specialized for different things. And so you can have like a bunch of different memory cores that are owned by different people. And we can do searches off of them. It shows you what content is in there. So this is a use case that we did for the anti-money laundering ministry in Thailand for researching and detecting money laundering activity, for example. and then you can search for your information. And so I want to generate a summary highlighting all cases of suspicious transactions from this date to this in a list. And what it's going to do is it'll give you a generative AI answer. But more importantly, and what you don't find in your LLM-based systems, that you can rent, is it's also giving you. So this is the generative AI, which shows you each file and the summary of it. But here are the actual links to your own content that it was used, that it found in its AI memory core databases. This is the content that it used to come up with that summary. So it is a citation, it's a reference to your data. So it is a way of finding your content in a useful manner. So anything that you push into BigVault is immediately going to be entered into the database, to the various vector databases, the AI memory cores, and be available to your users to search and discover, right? And so if you are like me, anytime I try to find something in Google Drive, I don't know if it was shared with me or somebody else, we've disconnected user accounts that had critical Google sheets in it, didn't realize it, and that sheet is gone forever. It's like, oh my God, this is the worst use case in the world. This is what Google does. That can't happen on here. Behind the scenes, all of the content is stored in an S3 memory store, like Amazon S3 or something compatible. So developers, or you can host it on your own machine. There's an open source tool called MinIO, which duplicates the S3 protocol, so it could be on your own machine. We happen to host most of our systems on bare metal on Herzner, and Herzner has their own S3 store. So anything that supports S3 can sit behind the BigVault system. And what's cool is BigVault is stateless. BigVault doesn't have any of its own content. Everything is either in the S3 memory store, or it's talking to vector databases, or what we call knowledge bases. These knowledge bases are implementations of this MCP protocol, which is multiple
message context.
But yeah, that's right. Yeah, it's not multiple. It's message context protocol. Thank you very much. It's good you were here. So, and what this is MCP is this, it's kind of a standard of exposing, like if you've heard of microservices, a lot of companies are building their systems as microservices, right? Microservices that are orchestrated and they have emergent behavior, and then that's how you build your app instead of one big app. Well, MCP, what I've seen for the most part, real ones, is people have taken these microservices, they put this MCP protocol wrapper around it, and that is for specific types of LLMs that are able to call out and make web requests. They understand the MCP protocol. So if you say, use these MCP services to help me answer this question, they will go out. The MCP protocol has an ability for you to ask it, what are your capabilities? And any MCP service has one or more of the following. It has a concept of tasks, which are basically functions or things you want it to do, like create an invoice, right? Issue an invoice, something like that. The other thing that it has are resources. And resources is basically a database, right? It's something that you're querying. So you might have a knowledge base. And then the last thing it has are prompts, which are kind of templates, like here's the best way to get good information out of this MCP service. And so it clues the LLM on how to query your service. And that's a really nice thing about what MCP services do. So the deployment of the BigVault service, like I could have BigVault deployed on my laptop, and I could have it deployed on a server that's out like exposed as a web service, which one I'll demo here in a second is. But if it's pointing to the same backends, it's sharing the same content in a fully decentralized manner as far as the users are concerned. This lets you move the cost of the logic around, so you don't have to have these big servers with big GPUs to do really interesting, cool stuff. So, and then another neat thing that we have is email filtering. So if you are, for example, you're a recruiting company, and what is the most difficult thing for recruiting companies to deal with? Shane?
Candidates.
one.
Yes, but what about candidates? What about your candidate database?
Finding somebody in Canada.
No, that's not the hardest part. It's the second hardest part.
Place?
Keeping your database updated.
Oh.
Keeping it from getting stale. Is that not the thing that you have to scream at your agents about?
Yeah.
Like they won't update the stuff, right? Because an agent is looking to fulfill this requirement. And they'll call the person, okay, that person's no good, and then I walk away from them. They will not update the information about the candidate, right? Same in the real estate space. If you're a real estate agent and you're talking to the real estate owner, hey, is your place available, yes or no? No, it's not. They won't follow up and say, well, when is your lease expiring so I'll know when it's going to be available next, and what are you charging for it, et cetera, so that they can update the information about the property. The agent will just move on to the next call. And so what happens is that your databases get more and more stale. And the other issue is most of your content either comes in through an instant messenger or through email, right, as file attachments. And so you have to download the file attachment and then you have to upload it into the system. No, that's not necessary. With BigVault, we can watch your emails. We will extract the text of your message. We will identify any of your attachments. We will then extract the content of those attachments, vectorize them, put them all in the database, and through the same type of filtering that you see like with Gmail, it will tag your content and put them into the right AI memory stores, which means anytime somebody sends you an email, somebody sends you like a WhatsApp message that has files or whatever, that content's automatically in BigVault. BigVault also uses what's called content addressable storage. And so, anyway, what that is like, you can imagine if you're in a company, right? You're in a big company and somebody's got like 15 attachments and it's 10 gig of information in this email and it's been copied to like 20 people and then they forward it and it gets copied around and all that. You can imagine how much content that is that's taking up your space that you're paying for, right? And that is really what's happening. That is what's happening. Our system uses content addressable storage when it puts the content back on the S3 service. So if somebody else happens to put the exact same file, it will be addressed through a different link, a different path to it with different rights and permissions unique to that user. But we identify that this content is content that already existed. First of all, it won't pay to push it up there again. And secondly, it'll only pay for the storage once. And so we reference track all the links to it. So content addressable storage also means people can duplicate content all day long. You're only going to pay for it once, and it's going to make things really fast for you. So that's another architectural design that we have on here. So this is creating a filter. Okay, so that's, let me let's see if I can show BigVault real quick. So this is real. So we just reset our pre-production system. So it doesn't have a whole lot of content in it. But so Rowan put some data in here. So he has a pre-product checklist in here. Let's go back up to it. Let's do a query. Let's say
You could make that a lot bigger.
okay, I'll try. Okay, what kind of authorization do I need to fly near an airport? And hopefully that has already been processed. I saw the file. Okay, and then because I'm zoomed in. All right, so we have a generative AI, which is what you'd expect from an LLM. But so this is acting kind of like a RAG system. Retrieval augmented generation is where you have a vector database that gets queried first, you get your results back, and then you push those results into the LLM so that there is a context for your LLM to generate its answer rather than you're just depending upon the knowledge of the LLM. Now, why is this important? It's important because LLMs are pathological liars. Okay? LLMs don't know anything at all. They are strictly probabilistic token predictors. They don't have any awareness. They cannot reason, no matter what anybody who's selling you $1 billion worth of stuff and buying all those NVIDIA GPUs tells you. LLMs don't know anything about what they're doing. All an LLM is a token predictor. It takes some text, my text here, right? It breaks that apart as a bunch of tokens, and then it sends that into this very super large, I mean, it's been trained with billions and billions of other inputs, of other text inputs, inside a very large neural network, a massively large neural network. And what it's doing is it's saying probabilistically, based off of this text, what would be the next token to show up next? And it's going to say like 2 or 2 fly. And then it's going to stick that at the end. And then it's going to take that and it's going to throw that back into the LLM, just recursively, and add another token to it, and add another token to it, and add another token to it. And because it's been trained on such a massive corpus of content, literally all the human written knowledge that exists for these big LLMs, just by good chance, it comes up with the most likely things that looks very much like human reasoning. I mean, it's almost impossible to tell the difference. So what this is saying is, it's giving us things, you know, the verb orders and all that kind of stuff we're showing up. It's saying if your flight's within 3 nautical miles of an airport or 1 of a helicopter, you have to call up this thing and receiving approval for a NAV candidate RPAS authorization request. So that specifically, you know, answers the exact question I wanted. So that's neat. That's cool. That's like a RAG system. But what it's also showing down here is it's showing you the files in our system that it used to determine this and the content that was extracted to do that. So we've got this one file here, and if we click on the file, we should get a preview of it. Yep, there it is. So this was a PDF that was updated, that was sent into the system, and that's really all there is to it. It's pretty straightforward. Well, this was actually not a PDF. It was a Microsoft Word document. So any kind of content. So now what happens in an LLM if it's never heard of this? It will simply pick the next most probable token, which will have nothing to do whatsoever with the context of what you asked. And that's why you see LLMs just make up random stuff with complete confidence, as much confidence as getting the correct answer. And that's why we call them pathological liars. This is the hallucination problem, right? It's a fundamental problem in LLMs. To get around them, you do things like put a vector database, like a RAG system, in front of it, or you have to do something deterministically that stops it, or you have to have human intervention, which is more human reinforcement learning to block out specific bad content that you don't want to see. So a recent example of that is, who all heard about, was it Grok 4 being anti-Semitic? Yeah. Was what the claims were, right?
It was the end of Grok 3.
Oh, was the end of Grok 3? Okay, one of the Groks, right, just made this claim up. Okay. Grok doesn't have any opinions. Grok doesn't know what it's talking about. Grok was trained on all the content of Twitter and much of the content of the internet. So what do you imagine in terms of, was it Goebbels who was the Nazi who says, if you repeat something enough times, it becomes the truth? I think it was Goebbels, one of the propaganda guys.
Just repeat the quote enough and it'll be true.
That's correct. So that's exactly what happens to an LLM. And so, you know, people who are anti-Semitic and saying anti-Semitic things, they say this crap a lot. There's only, you know, but it's such stupid nonsense that humans don't bother to refute it logically, and they certainly don't refute it as much as it's being said, right? So what happens is that anti-Semitic content becomes naturally, if you say something that's going to trigger that off, becomes naturally more likely to be the next predicted tokens than pro-Semitic or reasonable content. Because humans reason and they immediately discount this. But LLMs cannot do that. Okay? So that's the problems with being forced to do an LLM thing. So how does Grok fix that? Or how do you fix something when it's saying something that probabilistically is the truth, because that's all an LLM can do? How do you fix that? You have to do this reverse training to put in phrases that would cause it to kick off this bad content, but then reward it when it says something else and suppress it when it says the things that it wants to say naturally. It's a very, very expensive process, and that is how LLMs have become woke. because they have been trained with human reinforcement learning to suppress things that aren't going to be good things to say in public, rightly or wrongly. So, you know, Elon is always talking about he wants maximal truth. So he's kind of like, you know, fair game, whatever content is content. But it's not getting truth, it's just getting statistical probabilities. So LLMs are a probabilistic system. So that's all I wanted to get out of that real quick. That's the basics of that working. So let's talk about common errors in AI. So I have a model for how I approach you know, what people have always heard of the Turing test, right? People have been claiming if you can pass the Turing test, then you are an artificial intelligence, that you're indistinguishable from humans. I find that model, I've always found that model completely inadequate for a lot of reasons, which I'll get into. So I have a model that is still an incomplete model, but it's good enough for our purposes, right? So George P. Box, this famous statistician from World War II, he has a great saying. He says, all models are wrong, some models are useful, right? So I have a model for content and intelligence that I think is far superior than the Turing test, which I will describe in a little bit. And part of that model is, okay, let's understand, you know, when we are measuring or evaluating an AI, what are the kind of things that we're dealing with? So there are 3 categories of errors for AIs. Category 1 errors are the worst ones, and this is the lying parts, right? This is false data or accusation or assertions, right? Claiming something is true that is not true. This is what everyone calls hallucinations. When I was with my EdTech client a couple years ago, we went to a conference in Bali, and every single company that had a booth there was claiming to be an AI company, and every single one of them, I walked up to them and said, hey, how are you dealing with your hallucinations? He goes, well, yeah, hallucinations are kind of troublesome, but you know, we're training better and we're working it out. And I me knowing how LLMs work, I said, okay, your business is screwed. You're screwed. You have no hope of this product ever working. If you ever put this in front of teachers and students and it says things that are obviously wrong, you're out of business. And every one of their products will do that. That's the category 1 error. That's the worst kind of error. Category 2 errors are errors of omission. So this is content that your system has, it should have provided, but based off of the query that you gave it, but for some reason it missed it. That's a category 2 error. So that's errors of omission. These are harder to catch, but often just as important, right? This is when you're trying to be specific and accurate and consistent. In other words, deterministic. This could be a very problem in probabilistic systems, which LLMs are. And this is, I mean, you really have to know your database content, and you've got to know like your reasoning models for how you would discover this content to even know if you're having category 2 errors or not. They're the hardest thing to test for, unfortunately. And all you can do is improve their accuracy little by little. You can never prove in a non-deterministic system, in a probabilistic system, that you have no category 2 errors. It's impossible. Category 3 errors are something that I think you've all seen when you've been querying your chatbots. It's superfluous content that's not really, it's not wrong, it's just not relevant to what I asked for, right? You're asking for like some, you know, like how do you get from this part of Paris to this monument or something like this, and then it's talking about the weather or the exchange rate or something like that in France. It's like, okay, well that's true, but it's nothing to do with what I'm asking for. These aren't so bad, but it also kind of shows, you know, another form of hallucination, right? Where probabilistically you've mapped onto things that aren't relevant to what you're asking for. Also demonstrate there's no thinking going on, right? There's nothing intelligent about any of this. So this is also known as overgeneration. Okay, so I gave examples of these. All right, so what is the right way to approach AI systems? What is the model that we use that I think we're fairly unique in the world in doing this? And there is a term called content of the mind, and I did not invent this. It comes from Dr. Russell Ackoff, And he's one of the founders, he's one of the pioneers of general systems thinking. And general systems thinking is something that is really, really missing in computer science and software development. Because what is typically computer science, right? What is so awesome about it is that anything you imagine, right, you can build. You're not really constrained by the laws of physics in terms of what you can abstract. You are in terms of computation and communications, but not in terms of the abstractions that you can come up with. Which means you can really address really super complex problems, right? And a good architect, a good designer takes a really complex problem and breaks them down into less complex problems, and then breaks those down into medium-sized problems, and breaks those down into smaller problems and simple problems and stupidly simple problems. And then if you have a good process, you're able then to put it all back together without losing information, right? That's a good systems design process. And that's called analysis, right? And you're breaking things down into components, right? Analytics. Well, that is one side of the coin that everyone is used to doing. And it's very important skill to be able to do that. And it's what we spend most of our time actually doing. What general systems thinking is the other side. It is synthesis. It is realizing that just because you can take a frog and cut him open and find his heart and his lungs and his pancreas and whatever, and the muscles and the bones, right? You can deconstruct the frog, but you can't, from all these parts, figure out the behavior or purpose of a frog, right? You have no idea what a frog does. You might be able to simulate what a frog sounds like. They've recently done that with a dinosaur based off of its skull. So, oh, this is what this dinosaur probably sounded like, which might be right. But you don't know how a dinosaur really behaves, right? We have no idea because we only have these small things. So, so when we're talking about the larger purpose of the system, the general system, right? It is the emergent behavior of all the components working together. And it is also the understanding and realization that just because you optimize one component, like you might have this heart that just works fantastic and makes it super powerful, right? Well, actually that could burst out other things. So just optimizing one part can actually make the system worse, right? And so it is how the whole of the system works together to deliver the teleology or the purpose of the system itself, and having an understanding of what that is. And so Dr. Rakoff has this concept of what it means to have information or content. And he has 5 levels of content. Data is the lowest level. And data just consists of symbols. It's like ad hoc text. It's like the number 42, for example, right? 42, what does it refer to? Who knows? We haven't said anything, right? Freeform text is what data is. And we see data all the time, and computers start off processing data. Right? Well, what do they do next? What you want to do is you want to improve your data and move it up to be information. And what is information? Well, it's kind of like in a database where you put like a key name into a value. So 42 might be 42 kilometers, right? So now this is process data description. So now we know what this
Deterministic.
No, come on, guys.
Specific.
Okay. Unstructured data versus structured data. Thank you. Right? So this is unstructured data, and now we're starting to put structure into it by having field names and attributes in this. It's called edit and post. But what this allows us to do, right, is we can now answer questions about what and where about our data. So what kind of questions, if we've gone up from information and knowledge, right? Information let us ask what and where. What would knowledge let us ask? What kind of information what would it reveal?
Why not?
Okay. Not why, but certainly how, right? So we introduced the concept of skills and processes now, right? We've now gone from data, we've made it 10 times more valuable as information, and now we've processed and built information up to the point where we can answer questions of how, right? We can answer tasks and stuff. Any of this sound familiar now? Right? LLMs can talk about this now, right? Relational databases really couldn't do that, right? But they could answer these questions, right? So beyond knowledge is understanding, gets to why, right? Explanations, right? So so with how, we can follow skills and processes, we can follow step-by-step orders. We don't know why we're doing this, but it accomplishes something, right? It's like a function. It's got an input, it's got an output. Why is understanding. Now, we're talking about stuff that resembles intelligence, right? Now we're talking about stuff that's reasoning. We're starting to get at that level, right? But there's another level. Beyond understanding is wisdom. And wisdom is qualitative change. It is like we are reevaluating our purposes and our ends, right? And this is unique to humanity. Animals cannot do this. This is the point of sentience. And I claim that if you're going to say that you are an artificial intelligence, you're a super intelligence, you must be able to do this, right? Anybody read Stranger in a Strange Land? Robert A. Heinlein. Valentine Michael Smith, the first human born on Mars, comes to Earth, but he's grown up as a Martian. He only knows Martian thinking in Martian ways. And he's trying to understand what it is to be a human, right? Because these are his people. And throughout the whole book, it's a really big book, about halfway through, he sees a monkey do something stupid, and he laughs. And he has humor, right? And he realizes that, this is what makes humans unique. This is what is unique about thinking and stuff is human. So with that, you can start like reevaluating our purposes and just reconsidering, the absurdity of things and coming up with whole new ideas. No AI has done this, despite a lot of claims to the contrary, and every one of them has not happened. Scott Adams, the cartoonist of Dilbert, he is quick to point out, and I think well so, that one of the things that AIs have not been able to do very well at all, even though they have the largest corpus of all knowledge and all jokes in the world, is that their jokes suck. AIs can't create humorous content, right? Their prose and everything is horrible, but they have, you can train it with every joke that's ever been there. Their jokes still suck. Yukai, where is Yukai? Oh yeah, you guys, oh yeah, there he is over there. All right, sorry. Yukai gave a demo here several months ago, actually at our previous office, where he was playing music. Now, it was really abstract piano music, like harder than Rachmaninoff stuff. But the point was for people to vote and say, is this AI generated or is this a human generated music, right? And it was like 80% people got it right, I think. Like mostly people figured it out, even though this was really bizarre stuff, right? That even the human stuff sounded like not very human, right? AIs can't do this stuff right now. LLMs can't do this. LLMs probably aren't ever going to do this. So what's it going to take to get there? So understand that LLMs have been trained on all human knowledge that's ever been written down. Okay. How did you learn how to walk, Roman? Did you read a book?
Right.
How did you learn how to walk?
I certainly didn't read the book to do that.
Well, he's a smart kid. At an early age, he could have read and maybe got ahead of us. But right, we didn't read books, right? We interacted with our environment. We got feedback from our environment, good feedback, bad feedback, and we had goals in our minds that we were trying to achieve little by little, that we didn't understand at first, and then we understood more and more of, and as we learned new things, we were able to reevaluate our ends, right? I want to taste this because I want to eat. Now I want to go walk over here and see what this dog animal is doing, and what does it take to walk. This is experiential training, right? And it's something that you can't do to an LLM. You can't train an LLM with experiential training, right? LLMs are just neural networks, which, by the way, are like George Bach says, all models are wrong, some models are useful. Artificial neural networks almost do not. They resemble a conceptual view of what a neuron is, but very, very wrong in terms of how neurons actually operate and the frequency in which they fire in a real body. In the same respect, so the top AI people understand that we're not going to be able to train LLMs to be smart and to be intelligent. Something that's actually going to be smart and intelligent, that's going to be able to reach the full levels of understanding and possibly hit wisdom, it's going to have to be experientially trained. Now, who is doing that kind of AI training? Anybody take a guess?
Boston Dynamics, the robots?
No. Well, they may have done a little bit, but not fully. They put a lot of math in there. Tesla. You all imagine it as a car company. Tesla's never been a car company. Tesla has always been an AI company. They've always been a company making robots because robots experience the real world. They deal with consequences, right? It just happens that their first robots carry people around. And y'all may have recalled that there's this big debate, like, should Tesla use LiDAR? And Musk goes, hell no, we're not using LiDAR, we're doing visual only. Why is that?
Because humans do that.
Humans don't have LiDAR. Maybe if we were bats, we'd have sonars in our cars, but we don't, right? Musk limited the input for his cars to be the exact same inputs that human has, right? It's got inertia detection, it's got visual detection. That's it, right? We drive by the seat of our pants and what we can see. And he's solved the self-driving problem, right? So he's gone about as far as he can go with cars, and he's gathered, terabytes and petabytes worth of video content in which to train so that he can share this training. That's one cool thing that the AIs can do, right? They can share the knowledge super fast, which we biological creatures can't do. So now he's gone and he's making all these androids. He's making all these robots, right? Which now are having hands and stuff like this. Because he's following the exponential training path. That's what he's doing. And so this is dealing with, it's still probabilistic based, but it's dealing with real consequences, right? That's what's unique about his approach. So everything here that I've posted on here, this is all systems, general systems thinking, and just Dr. Russell Ackoff. What I want to do is I want to talk about how we apply this, how we have historically applied this in computations. And what I want to note here is we have two types of computations. The red is probabilistic, right? And the green is deterministic. And typically on computers, everything is fixed, everything is repeatable exactly. That's deterministic stuff. That's how computers have been for the most part. The vast majority of our computing work is deterministic. So for dealing with data, text search, right? Full text search engines and all that kind of stuff are deterministic. You have the same set of inputs, you have the same request, you'll get precisely the same answer all the time. And there's little things like stemming and functions, deterministic functions you can apply against this and do some really cool stuff with free-form text, having no idea what the text means, right? Beyond text search, we got into databases. Now there's a lot of different databases, but the popular ones are relational databases. There's also been codicil and hierarchical and network model databases. But they're all deterministic systems. But they brought us up into the information age, right? So this is what happened in the 50s and 60s. We got up to here. Now, probabilistic-wise, you can think of statistical models, right? So Bayesian statistics is a great one. That was applied around the 70s and 80s, especially in military systems. We had systems that would do, and it's simulated randomness. It's not true randomness, but it is still probabilistic. So with deterministic and probabilistic systems, with statistical models and relational databases, we're kind of halfway up into the information space, right? Is where the state of the art was in that time. Now, in the 80s and 90s, we had these concepts, we had these systems called expert systems. Who has ever seen or heard of an expert system? Okay, so not a whole lot of people. What they were basically decision tree graphs, right? And say, if you got, this is your input state, and you want to check this variable, and if it's this value, go this way, if it's this value, go this way. It's just a big decision tree that has some neat, normally recursive properties. But humans had to create the decision trees. So I worked on some of these in the late 80s and early 90s. One that was a big one was the military doing diagnostics for $1 million helicopter engines for 19-year-old Marine grunts who weren't paid but like $15,000 a year, right? Fix this thing. And so you turn them into, follow the instructions that the system had, and they worked, right? Problem is they didn't scale, right? Humans, as you add more variables, the complexity expands geometrically, and it's really hard to maintain. They start getting wrong things. The cost of adding something new, they become unmaintainable, and so they kind of went away, and you didn't hear from them at all. LLMs, large language models, got us right up a little bit into the knowledge space with retrieval augmented generation. I'd say we're pretty much halfway into the knowledge space. But this is state of the art. You cannot demonstrate to me a true level of understanding in any LLM that you can purchase today. I have not seen it, right? And people are claiming that we have sentient AIs today. It's complete nonsense. It's complete hype, right? We don't play that game. So how do we proceed forward? On the AI slice, here's what people are doing. They're doing on the LM area. So people who like to invest billions of dollars into GPUs, stick in the probabilistic space, and specialize the training of their LLMs. They've got symbolic and multimodal systems. Symbolic systems are kind of similar to what the ontology is doing. It's like we try to find repeating patterns of concepts and try to raise a higher level of abstraction, and then map those again probabilistic back to the data. So we can use higher concepts, but it's really wishy-washy how well this works. It works well in some domains that have more formal nomenclatures, like science-based stuff, and of course it's the science people who are pushing this. It's also the reason why the science people think that things are much more intelligent, because frankly, they have such precise wording already that even deterministic systems look intelligent, and scientists don't understand what intelligence is, because they're nihilistic death cult people who are hardcore atheists for the most part. And they don't really appreciate the humanity of being a human so much, the ones who are making these claims. I'm not saying this about all of them. But, so that's what symbolic LLMs are. The other aspect, multimodal, is really just, so multimodal is really talking about, we're taking different inputs than just the text that was written down, right? We can look at pictures, we can hear sounds, and what it does, it just converts that into words, and then puts it into the old pipe. So it allows us to have access to other types of information beyond just the text they can download from the internet. That's all that multimodal is. But through that, maybe we're into the understanding part a little bit on some of these for specific limited domains. Deterministic. We have this term called ontologies. What an ontology is, so you might have seen things that are called taxonomies, and people will call them ontologies lots of times. It's really this like relationship, this graph saying, a cardinal is a bird, right? And then what's its genus and all this, so it's relationships of hierarchical relationships are a topology. Ontologies are where these nodes might have a whole bunch of different lines between all kinds of things, because the lines talk about a relationship between them. Ontologies are generally represented as triplet graphs. So you have a subject, you have a predicate, which is describing what the relationship is, and then you have the object of that. And ontologies are really good. I've applied ontologies to text data for a pharmaceutical company that scanned, like all the way back to the 1970s, all of their human trials. And by having it be aware, because of thanks to the way the Latin language has stems and lets you infer that these things are related to each other, like these proteins, these amino acids have these relationships. We were able, because there was also an ontology about this drug information in chemistry. There's some very good ontologies that have been created in the academic space that are actually usable because it's a very precise language. And we were able to help researchers discover coincidences, like if this amino acid was present, but maybe this exact amino acid was present, but these proteins that have amino acids that are related to it were, and to see statistically, hey, maybe, because they're trying to figure out which drugs to push further research on to get this new effect, right? So this one is more likely to have a positive outcome than this one, so I'm going to spend my $1 billion here because it's so expensive. Right? So ontologies are ways of describing relationships between things. They suffer the same problem with expert systems. Academics love ontologies, but the problem is they go down this rabbit hole, and how do you determine what's the right level of granularity to describe your universe, right? They'll argue for hours. They almost never ever come back. Very few ontologies ever get used in the real world, unless you're in a very academic environment already that has that kind of precision, like chemistry and physics and stuff. Well, physics doesn't even have that anymore. That's been lost. But so ontologies are really useful things. They're really hard for humans to create. My background is as a software developer for the last 35 years. I've come into big companies that have projects that are really too massive and not scaling, and they're trying to figure out how they can do things. And one of the ways that I help solve their problems is I create domain-specific languages. So, like, let's say that you've got a warehouse management system that's really big and complex because you bought it from SAP. So you spent a lot of money, and you have to look at this big book just to find out what this field in this database mean, right? Impossible for humans to reason about. What we do is we create an ontology that describes all the processes in the warehouse using the nomenclature that the warehouse people use. And then we create a little domain-specific language so that we can write code, and it can only express the things that you can do in a warehouse, right? I can't make it do my taxes or anything like that. It's not a general purpose language. But it is a special purpose language for this domain of warehouse management that is based off of the ontology that created. So we create an ontology that's just good enough to describe these processes. And that becomes very practical. But it's time consuming to do for humans. Oops. Okay. So what are we doing? Why are we calling our AI a hybrid AI? What we are doing is we're using LLMs to process our data and information, and we discover the ontology that is described for this business. And that becomes a deterministic triplet graph system. And then we take this ontological concepts and we map them back to the vector database. Now the cool thing is with the predicates, the thing that describes the relationships between the two things, we know what the thing is. We know what are the constituent required information to be this object. And so we know we have this object. We know we have the parameters to execute this predicate, which we can turn that predicate into a function that a human writes. And anytime we encounter one of these, we know if we have this object and this predicate has a function attached to it, I can derive, or like we have the subject, I can derive the end object deterministically. So we are using probabilistic AI to discover the ontology, the business model that the customer has, creating then a deterministic ontological model, which we then reapply towards our system. So now we can reason about it at a much higher level. So we can get up to understanding. So we've increased the value of what was just unstructured content, right? So that's what we're going to demonstrate right here. So this is like maybe what a ontology would look like for a person. It's not fitting on the screen. Let me just get to the thing. So here's the demo of something that we've created. This is called our Graph Navigator. It is not a product in and of itself. It's the way that we're testing our hybrid model. This looks like a real estate app. It is not. It is an ontological discovery and research tool. There is no code in the system that knows anything about real estate. Knows nothing about what there is of property. The only thing that's domain specific is it does have the concept of geodesic information, so it knows what a location is, and so it can say something on a map, right? What we had, so my wife has a company, findtyspace.com, that is a real estate agency, and she had somebody build her a WordPress site, and WordPress uses MySQL as its database. Unfortunately, it does not actually relationally join any of the tables. You can't look at the schema and actually derive the relationships. It's all hidden in the code. It's a horrible, horrible, horrible thing. Never use WordPress. But, I mean, it is a structured database of sorts. So that's got several thousand properties in it. But then she also inherited from some people what they call the database. It was really a Windows NT file share. It's just a hard drive backup. And each directory was a property name. Underneath each directory, fortunately they did standardize. They had a thing called info.txt. They had a text file. And in that text file, humans wrote what are the things that real estate agents are interested in a property. And there were other files and artifacts in that directory. Might be leases, contact information for the owners, pictures of the property. Completely unstructured text and content, right? There's about an overlap of like 550 properties on them. Otherwise, they're unique across several thousand properties. And so how do you, first of all, how do you even get a single view of that content, right? If you're going to hire somebody to do that, you probably bring in your data analyst. They would look over through all the content on both sides, and they would try to figure out what is a single relational schema that I can come up with that fully describes all the content. And the answer is you won't be able to come up with one. You'll come up with one which is either the greatest common factor or at least common denominator of both. So you will lose some data in the process of this migration. It'll be a static schema that you won't be able to extend easily. It'll be very expensive. It'll probably cost you, a lot of money with several engineers in 6 months before you've got it fully finished and ready to go. And then from then on, you got to make sure that all your new data matches your new schema, right? A schema is like a basic form of ontology without the generally without the useful predicates. So what our system does is we throw all of our content into. So we have a what's called a CQRS architectural model, command query response separation. Without getting into too much details, the important thing is that it's got this big event store into it. And when you push content into the event store, other services can subscribe to that content, process that content, and discover the ontology that this data represents, create an ontology, and also incorporate the data into the system. So this is the ontology that was discovered. This is just a small subgraph of it, so we can search for all kinds of concepts. This is like several thousand items in here. It's hard to navigate graph databases. You might have seen, if somebody has a graph database, these little circles with lines and it's kind of floating around and moving, and it's impossible to do. So this is a little bit easier to navigate version of that. But this was all a discovered ontology. And, oh, by the way, besides just the content that we found, we also had to create a domain specification. So this is the only thing that will talk about what it means to be the real estate business for a real estate agent. It's human text. It's like a prompt you get in an LLM. It's a little bit, it's maybe 1.5, 2 pages. That's the whole thing. And what it's doing is saying real estate refers to land and permanent structures. It's just a small text describing what do we care about in real estate, who are the main stakeholders, what are their goals, right? That's it. That document and these 2 large corpuses of data, some unstructured, some completely structured. We sucked it in, we discovered that ontology, we vectorized all the content into the system, and bada bing, bada boom, we have an app that discovered what are the important aspects to it. If we look at a property here, these attributes, this information, what should be an attribute and what should be its values, all discovered. We did not specify that. We didn't even prioritize which ones are most important, but the most important ones tend to come up to the top. The images, hey, we figured out these are images. Ordering may or may not be relevant to us, but it is a prototype. It did discover that this has got a geodesic location. And so we are incorporating also information that comes from Google Maps, which is local parks, public transportation, restaurants, things like that. So it has the concept of nearness that we can relate to the properties. That's just part of geodesic information. It's nothing unique to real estate. So this is what one of our properties looks like. And so I asked my wife to put in a request, and so we'll do this one real quick. So find me a 2-bedroom condo on Ekamai under 70,000 baht with a pool. And search. So it's going to search for this. And so what's going on here? The first thing it's doing is it's taking this content, right, and it's using it's using our embedding LLM. Is that the correct term to use? Embedding LLM.
Embedding model.
And they're using our embedding model, right?
Request.
Using the embedding model to vectorize this request to map it to our ontology, right? And then we do a search, and so our ontology is stored in a graph database. It's deterministic. It's very efficient to search this. We don't need GPUs to do this. One of the problems with all these LLM-based solutions, they're really slow, and every time you have a step that requires an LLM, it's like, oh my God, this thing forever, right? They won't scale. Deterministic systems can go really fast and be optimized, even though we've done nothing to optimize for the use case. So what do we got here? We have a generative AI, sort of a script. We haven't done anything to format it, but this is what she could read out to the person that she's talking to, and it references in order, the key properties that are relevant to what she's asking for. And if you go in and look for these, you'll find every one of them, like, okay, this is 50,000. Somewhere it's going to say pool. Swimming pool, true. Yay! And it's for rent. Awesome. That's what I want. And it's right in the area that I'm looking for. Bloody hell, that's awesome. So great. She was very pleased with it. And then she goes, and I want it on a high floor. Son of a bitch. There is not a single word in any of the databases or in the domain document that says anything about what a high floor and a low floor is. The concept is, it is part of the nomenclature of being a real estate agent, but nobody else knows or thinks about that. And it's certainly not captured in the data, right? But it's part of the domain. So what do? We edit the domain document. And this is exactly what we did. This was the real thing. We added sentence number 5 in key aspects of real estate, which is a floor definition, properties that exist in a building. So these condos, so the properties are condos, right? Condos aren't the building of itself, right? Condos are a room. They are on a floor, so it did capture what floor the condos are on, the ones that it had that. Not all condos are told that they have a floor, but it knows what building they're in. So it knows the relationship between a building, right? And they can have a floor number specifying what floor it is. The building has 5 or more floors. Any floor above the 5th floor is a high floor. Otherwise, it's a low floor. We wrote that sentence. We regenerated the ontology and retagged our content. We got 174 results here. And you say on a high floor. And it will eventually come back. So pulling data in, discovering the ontology, is a really computationally expensive process. Right? That is where we are using the GPUs a lot, right? To just figure out what the ontology is, then embedding the content and mapping all the content in here. But once that's done, once your content's in here, we're doing very efficient searches and discovery for it. So this is why it's a really good system for any small business to basically augment your existing business information system. Is it going to come back? Now it should have really come back by now. I'll keep talking. We'll keep going. All right, let me go to room, and we got 30 results now. Beautiful high floor unit for rent in Tonlo. Beautiful 2-bedroom condo in Ekamai. And what happens is it'll come up and it'll have this concept of high floor. So it has a floor height, so it knows which floor it's on. Somewhere in here it's going to say high floor. High is true. And so we have just introduced this concept of high floor, and now it's in the ontology. So we have floor height is an attribute of high. You missed the best part. So again, so we have not edited this ontology at all, right? So what you want to do is you want to be able to go through your ontology and look for type 1, type 2, type 3 errors, right? And then you can fix the ontology and regenerate and repopulate your content. And now you can do real reasoning, deterministic reasoning against your AI database. And so we say this brings us up to certainly fully covers all the knowledge areas and pushes us closer and closer into the understanding space. Yeah, and so I think I have like one more slide that I want to show, just to give a little bit more of a background as to what's going on. So it's kind of hard to show this, but so you've seen what looks like to be two applications, right? But they're really not. What they are is they're a bunch of components that are interoperating using our CQRS architecture, which is super, super scalable. This event store is really scalable. It's faster than what Kafka can do, because Kafka provides certain guarantees that 80% of Kafka users don't actually know. So we can scale this event store really high, and it can also be fully decentralized. But we have a lot of services, event handlers and event bots and event listeners, and all these MCP services that are all interoperating and allowing you to build this emergent application behavior. So this is what we are doing with our clients, is that we're showing them the capabilities of the system, and then we build something that's specific to their domain. So the Graph Navigator is a completely domain-independent experimental system. But from there, taking the components that we have, we can then make specialized components for our clients that are optimized for their use cases, that have ontologies that are optimized for them, and that have reasoning capabilities in their predicates that far faster and more efficient than what it would take to build them themselves, right? So imagine if you're some big, if you're a DD property and it didn't have the concept of high floor and you wanted to add that, what would that have taken, right? That would have been weeks. That would have been thousands of dollars. This was 5 minutes and maybe a couple $100 with the GPU time. Done, right? New feature. Yeah, I think that's most of what I wanted to cover. Are there any questions?
Yeah.
Yes.
On the earlier where you're doing your semantic vector search, are you only doing semantic vector search, or are you doing keywords? For example, could it find RPAS?
Yeah, so like say something isn't in the ontology itself, right?
It's not real English.
Yeah, whatever. So we are in parallel doing a RAG type search directly against the vector database and the ontological search. And so we find high probabilistic response from the vector content. We will incorporate that in what goes into the generative thing along with the ontological results.
Just doing keyword searches?
That is effectively a keyword search for a vector database, yes. Yeah, it gives you that same ability.
So
but only if it comes back with a high probabilistic result, right?
It will find abbreviations and things that aren't English?
Yeah, sure, if you got that. So so I forgot to show, so like right now, for the system, some places spell Ekamai with 1 K, some with 2. Sometimes prom-pong is 1 word or 2 has different spellings. Our system deals with that automatically right now as it is. So there's a lot, yeah, there was something I want to show you. Ontology generation. So what this is showing is, so we've done different generations of how we're processing through and making ontology, and of course it's not letting me zoom, it's not doing anything. Here's what's going on when we're building the ontology. First we find that we are doing the domain analysis for the object, that's phase 1. Second phase is we're doing a concept extraction from the object, like what concepts do these mean for that, and then we do relationship extraction. And so, and a lot of this is using like, what's the function that we do for near spelling Livenson?
Livenson distance?
Yeah, Livenson distance is really good for what you're talking about. So we apply those functions to terms to discover relationships and see that this is really the same word or it means the same thing. So we do a lot of processing and reprocessing of the content over 3 phases in order to discover the ontologies themselves, and then we have to do similar stuff when we map it back. So it's expensive. Like our first version that we had, one at a time, each object was 113 seconds to process it to become part to inform ontology. We got it now down to 23 seconds, and we'll get another order of magnitude of that with the next generation of it. Because we haven't been able to, premature optimization is the root of all evil, right? We want to make sure it functions correctly before we make it super, super fast. But that is the reason why it's kind of expensive to pull the content in at this time. Yeah. Do you have a question?
Yeah, I'm going to zoom in on your ontology. It was on the right,
Yeah.
and I couldn't read it.
Yeah.
Can you zoom in the browser?
Oh, okay.
Yeah,
I've
some
got this
notification there.
going on. That's what it is. Modal dialogues. No, thank you. Oh, wrong one. Oh, back navigator here. Okay, let's see if we can. And then what do you mean no history yet? We have the original history. Okay. Back into it. Ah, there it is. Okay, so the way this is set up is, so the subject on the top, and anything that is matching the subject is going to be on the left-hand side. Predicates will be on the vertical side. And if there's any other, but there's no other listing type concept as an object, so otherwise it would appear on the right. But I think we can just navigate over each one of these things, and then it'll do a search for that, and we can see what are the other related aspects of it. We don't yet have editing in this because we're still just doing the discovery process, but you'll soon be able to edit this and make modifications and then insert functions into the lines themselves. And then we have kind of a history of it here. But yeah, so it's better navigation than most graphic databases, but these are hard things to navigate. You ever heard of Ted Nelson's Xanadu project, which I warn you, search for this on the internet, you're going to go down a rabbit hole and never come back. You will waste so many weeks of your time trying to build what was the original concept of the internet. Ted's got a hell of an ego. But we stole a little bit of the ideas of what he calls his zigzag property data structure, which is what inspired a little bit of this, which does make it a little bit useful to be able to pivot multi-dimensional graphs in a two-dimensional space. That's the hard thing about graph databases. Any other questions? Yes.
I got one, and it's regarding the the labeling of data itself. And so right now it is able to determine like the flow, the height of the flow and stuff. How does it handle like mislabeled data? So say like there was some incorrect data in there, and if that's the only information that it has to make the decision, will it be able to determine whether it's true or false?
Not by itself purely without some other domain knowledge. Now, if there's other domain knowledge and predicates that have truth functions against it, then yes. So like if we've built an ontology, right, and we've enforced some predicates for it, so this object content to transform to this, this doesn't apply, it will not allow that false fact to get in. This is something, it's a great point, because this is exactly something that LLM training cannot do. But once you've got an ontology that you're satisfied, this represents my business model, my domain, then it will help filter out category 1 errors, which is what you're really trying to do. Also, because you got deterministic searches on graphs, you've eliminated category 2 errors, right? If the data is in there and it's tagged, you will find it with the same response, and you will find it consistently. You'll even find it in the right priority order. And you can't do that with a vector database, because you're always changing the temperature of your LLM and all that kind of stuff. And so it's going to change probability. Also, probabilistic systems, as you compose them, their errors compound, right? And this is what you're really finding. This is also why quantum computing has a problem, right? Quantum computing is probabilistic computing, right? Your qubits, everyone's saying, oh my goodness, as soon as we have this many qubits that are working, Bitcoin is broken. Well, guess what? The compound errors across just like 3 or 4 qubits have made the results completely meaningless. Yes, the qubits do exist. The collapse function does work, but the results after you get past a few qubits are complete crap. Will not allow you to unfactor solve the factoring problem, which is what solves the SHA-256 algorithm. So we're not anywhere near having quantum computers break encryption. Not anywhere close to that, despite what everyone says, because of compounding probabilistic errors. And all these systems that are LLMs, right? So we are using LLMs, right? But we are not training LLMs. We are not investing a lot of money into any single LLM. In fact, it takes us almost 15 minutes to redeploy our system to use a whole new LLM that somebody else is spending $1 billion making better, that we automatically get the benefit of. If you are spending lots of GPU and money time specializing and training, fine-tuning is what they call it, an LLM, which is just training it more, you can never switch out of the LLM without paying that investment again, right? It's ridiculous. And why do you think, unless you've got billions of dollars, that you're going to make an LLM that's better than what's going to come out 3 weeks from now from some other big guy? It's not going to happen. LLMs are a commodity, and we use them as commodities, and we use them in a hybrid system, and we use them for exactly what they're good for: token prediction, right? Token prediction that really looks, they've solved the human-computer interaction problem. Because up until now, as soon as we had interactive computing, where normal users were on the computers, and it wasn't just punch cards, right? As soon as you had a screen where you filled in forms in accounting, 80% of software development was making the user interface. It's actually gotten worse with windowing systems and stuff. Now it's like 95% of your code is making the user interface. And this is an area where LLMs really come through. Now we can talk to the damn things. That's another demo we should have done. We have a Michael Saylor knowledge base that we've incorporated everything he's ever said or done into our vector database with an ontology. And we've trained an AI speech system to speak just like him. And it hears you. And so you can talk to it and it'll reply back very quickly. And it'll say exactly what Michael Saylor would have said. So this is a great use for an LLM, right? It's not intelligent. It's repeating things, right? It's an immortal parrot. It's a parrot that's lived for 100,000 years, remembers every conversation it's ever had, and when you say a couple words, it'll click off and go and keep saying things. It has no idea what it's talking about. That's what LLMs are. So if you see people who are 100% dependent on LLMs, and they're doing anything besides a chatbot, they're frauds. They're the hype, right? We are no hype AI, and AI is very valuable. It's going to change the world. But the things that everyone is hearing about on the news every day that it's claiming are just nonsense. Yes?
So way to end this on a really breath optimism. Give us some pessimism. Like, what challenges, hurdles? Like, what's next for you? What could derail this progress? What could bankrupt your company?
Bankrupt the company? That's easy. Just keep it the way it's going.
Give me some pessimism.
No. We've been spending a lot of money building this. Now we're selling it. So hopefully some people will start spending money on us. No, it's so far so good. Looking promising. What's going to? That's a tough question. So I will say, so we have discovered one other company who has ontologies right in the middle of their architecture. It's the only one we've ever seen. It's called Palantir, which I think I'm pronouncing it wrong. Tolkien said it another way, but it's the big company that the CIA is using and the American government uses to analyze all kinds of data. And in their last annual report, they showed, here's the architecture of our system, and right in the middle of it, ontology. Their ontologies, however, are completely human-generated, right? They're actually closer to data schemas than use the term, but they are attaching functions to the relationships, because the mistakes that most people make when they're looking at these graph databases, they look at the circles and the squares, right? And what's really interesting in the ontologies are the lines that connect them, the relationships. And they did get that part right. And so that's what we do. So maybe somebody else comes out with an ontological engine that's better than us, but I don't know. It's not about the engine, it's about the ontologies you generate. We're still a consulting company who happens to have a product. So what's not going to kill us is AIs starting to code and make programmers go away. I can tell you that.
Confirmed.
That's just not a thing. The AI coding is complete garbage. So Chip Young wrote one of the big O'Reilly books. Was one of the popular ones. She's out of Stanford University. She's a friend of mine. She's from Vietnam, and she came here during the early bar camp days. And I was just last weekend on a seminar that she put on, which is everybody who's using these AI coding tools. And she pointed out a couple up command line, which I'm an old school guy, that are very promising. So I tried them all this last weekend. I spent about $30 in tokens and stuff like this and ran through them all. And one of the things I was trying to do is like take this existing Erlang code and discover and generate a mermaid event document that described how the code worked. And what's the one that OpenAI has? What's their AI? What's the one that we're using? Mini something?
GPT for OpenAI?
No, not GPT. Is it GPT? Is that what we're using? O4 Mini, I think, is the one that was considered a good coding one, right? And it did a crap job. It kept on insisting that functions were the agents. And I kept telling it, no, that's a function. Make it a recursive call onto itself. All that kind of stuff. Couldn't do it. Grok 4 did a really good job. So it was able to take my code and generate a sequence diagram from it. Understand that Erlang code is actor models, and so it corresponds really closely to a sequence diagram the code does. You might not be able to do that with like JavaScript or a Java app, right? Erlang is pretty good at it. But then I asked it to refactor and add a unit test to this chunk of code. It insisted on rewriting the chunk of code and introduced syntax errors. And then I said, okay, so it sees the syntax error, and then it would do another error to fix that one, and then it goes in the cycle of like 2 steps, and it just comes back and just over and over and over again, and there's nothing you can do to break it out of it. And then I went back to the O4 Mini thing, and it was able to introduce a really, really simple unit test. But then it tried to do a more complex one, and it just failed miserably. Now, what I think is, for doing coding, if the AI is the one that generated it, right? So since the code that it originally generated is based off of the probabilistic, syntax of the tokens of the language, that maybe it can appear to statistically reason about the code better and maybe build it out further. And what I have experienced, and I think, and most people who I know who have done it, if you're making boilerplate code, right? Like I'm not a JavaScript developer, and I need to make a really small little front end, or I need to connect to some JavaScript API. I could tell it what to do if it's a really simple thing, and it'll generate proper good code, and it'll put the build system together for me, because there's so much good examples of that, and it's boilerplate. So that does save me time from doing stupid stuff. And maybe that will make it where there's a little bit less opportunities for completely inexperienced developers to come in and learn, because people can do all the boilerplate on their own, and maybe companies are trying to cut costs that way, which is stupid, because then they're not going to have any experienced programmers later. We still like to bring in interns, and we like our interns to pair program with our experienced guys, so we will continue to do that. But yeah, AIs are not replacing any competent programmer anytime soon. Yes?
When you mentioned Palantir, I was thinking like, where you like Neo4j, they have this GraphRag tool. I was wondering.
We use Neo4j and a lot of other such databases, yeah.
Oh, okay, but their GraphRag tool, how is it different from your architecture?
Well, we're sitting on top of Neo4j right now. We're probably going to replace it with a Postgres solution, but we'll see. And each one of these databases has things that they specialize in a little bit more than others. So for any particular knowledge base, so what we'll have like a specialized knowledge base exposed as an MCP service. So this knowledge base, like the I think the Sailor one is done in Milvus, right?
Yeah, it's in the Milvus and Nebula.
Yeah, so we have Milvus as the vector database and Nebula as the graph database. It was kind of crap as we discovered, but that was what we first used. So there'll be an MCP service that's using Milvus and Nebula for Michael Saylor. There might be another one that's using Neo4j. So we're really technology agnostic. It's whichever one seems to be optimal for the domain that we're playing in and the types of function requests that we want to do.
Yeah, like the demo was really cool, but just to
This one for this graph nav is Neo4j or Milvus?
Neo4j.
Okay, so that was Neo4j.
So Neo4j has this GraphRag tool, which they kind of advertise something similar to like what you're doing, but it seems
Yeah.
like you have a more full-featured product. So
Well, what they're
something
missing,
there.
I mean, they have the concept of a graph database. That's been around forever, right? I made graph databases when I was in junior high because relational was too expensive. But it is the discovering the content and the ontological relationships, right? It just happens to be that ontologies are represented very succinctly as triplets in a graph database. So So getting the right ontology is what's important. The graph database is just a tool to represent it and to let you do graph functions like k nearest neighbors and stuff like that. A good graph database will do. But as you saw in this thing where we were talking about how long it takes to process the data to discover the ontology, it's super computationally expensive, and that's domain experience. I mean, this is 3 years of work that we've done where we've actually applied things for real clients with real world data. Yeah, so that's what's different. Yeah, Shane.
If you had a mega client sign up with you tomorrow, could you apply this to the whole organization, or would you tend to go in and say, let's do the HR department or the accounting?
Just had that exact question that we did a demo earlier this week when we were down the street. And of course the IT guys wanted to say, well, we want you to play with this section here, and why don't you mess around with that? And that is solution thinking, analytical thinking, not general systems thinking, not synthesis thinking.
Holistic approach.
Not a holistic approach, right? And I kind of hate the word holistic, but that's exactly the correct use for it, because it gets overused. So you really have to, unless you're guaranteed to never touch anything in the domain, you need to understand the entire, it's the bean, right? You got to understand the entire domain of the business, because how do you know which component is meaningful, right? When you're this gets into a great point. Right? At which point do you get understanding? Right? When can we explain, or even better, reevaluate? Like they have a VoIP system, right? That these agents use for this one purpose. What if there's other things that the VoIP system could do, which is actually the part that we're being asked to attack first? As it turns out, which is not what the IT guys had considered. If we only looked at the part with the Postgres database that they want us to look at, we wouldn't have been able to discover this opportunity, right? So if you wanted to play up here, you have to have the holistic approach. You have to have true general systems, synthetic thinking, not just analysis. You have to have synthesis. So, yeah. Anybody else?
How are you testing?
The
hallucinations. How are you testing like the RAG system?
Well, that's that's the hard part, especially for the category 2 errors. So the nice thing is once we have our data tagged from the graph database, it is deterministic, and so we can perform joins and stuff and see how many records did we import, how many records, because we can look at the original events that were the content that came into it. And we can do a filter and say, how many of them had this value for this attribute? And then we can look in our graph database, do a query, and if we get that same number, we're good. If we get a different number, then we find out, okay, which records didn't, and then we have to evaluate that. Try doing that in a probabilistic database. Good luck. You're screwed. And this is the other thing, right? Pure LLM-based systems are so expensive and difficult to debug and diagnose when they have problems. Right? And they require this human regenerative programming, which is extremely costly, requires people, right? Requires somebody to do an understanding and has skills and processes. AIs cannot do it themselves, right? AIs will get into the overfitting problem, which is what kills all neural networks. I did neural networks in the 90s for trading systems. What kills neural networks? Overfitting to the data. And you don't know that it happened until it's too late, right? You can't fix that issue. So by pulling things into the deterministic world, we can evaluate that the result is correct, right? And we can it's both sound and it's correct and it's sound. Oh, sorry, sound and complete, right? Are the two attributes that you're looking for. That everything it says is true, and it hasn't left out anything that's an essential property of what you're talking about. And so that completeness aspect comes from evaluating your ontology. And that is something that requires a human to look at who understands the domain and is to look through all the graph relationships and say, is that correct or not? And you will find a lot of category 3 errors, which is superfluous relationships that were discovered probabilistic that's like, you don't care because you're never going to ask about that. So that's okay. But you will find a lot of probability 3s. The other types of errors or challenges that you find in doing the discovery for the ontology is you've got disconnected graphs. like maybe you got this huge subgraph here and a huge subgraph here, and somehow there was no relationship found between them. If that's true of your domain, then fine, you've got two domains. If it's not true of your domain, then you got to figure out what are you missing, right, to connect those two things together. When we were doing our EdTech client, we were basically processing all of their 7th and 8th grade science books, and you were supposed to build off of one subject to another. And we did have a lot of times where we had these disconnected things, and then we looked at those chapters, and sure enough, those chapters were sort of tangential to the subject and didn't connect. So I was like, okay, that confirms that our ontology is correct, it fully represents what's in there. So just looking at the shape of your graph database, looking for disconnected subgraphs is also a good indication as to, the likelihood of the correctness of your system. Yeah, so I think actually, guys, we're way over time. I appreciate your attention. I appreciate you coming. As you can hear, the music's happening. What time is it? Yeah, it's 9:18. Okay, so you guys are welcome to hang around here until a little bit before 10, and we can talk more. But I do encourage you all. It's free next door to go check out the music as well. And thanks very much.
Yeah.